Me. Okay, so it is time for inverses. Very good, very good. So we know how to basically solve AX equals B, right? Row reduction. We've done some work on how to do matrix wrangling, right? Advanced matrix wrangling. So we're getting the skills. So we're going to help you later in life. You'll be very surprised 20 years from now when you think, I'm glad I learned that. All right, but it's a beautiful story. So we like stories, and this is a great one. All right, so inverses. And I've just started some things off here, just the menu for now. So this is probably going to be about 4 somewhat small sections on inverses. They are delicious. And this is for square matrices. So let's make that clear. So square matrices only. There are some special things we can do with rectangular ones. As I've said, there's always a square matrix inside a rectangular one somehow. But we're thinking about square matrices only. Right, so that's important. Let's put a little thing around it. Right, okay. So the pieces we're going to go through, not all in this little section, but so good things about inverses. Identity matrix, this is the sort of fundamental to what we're doing here. How we use inverses to solve AX equals B, and then things that gives us. And I have to again forewarn you that we will not do this for large matrices, but it's very important theoretically and for small matrices as well. 2x2s, 3x3s. Okay, and then in a few sections we'll talk about, I'll give you I guess in the next one, the next piece, a how-to, all right? And it will be, and this is a great thing about this course, we'll use what we already know, Gaussian elimination, to find inverses. So I just want to give you an example that we'll come back to, because if you've given a matrix and you're asked to find an inverse, it's not obvious at all, right? So if you're given 3, what's the inverse of 3 this is about multiplication? No, it's a third, right? So a third times 3. If you're given 0, that's a little hard, right? So what do you multiply 0 by to get to 1? And that's going to be a very key thing for us when it comes to matrices. All right. So let's just do this multiplication. Let's do some good things. This is a 2x2, 2 rows, 2 columns, a 2x2, square matrices. The first one has a prefactor, and I'm going to say that this is our matrix A. And if it works out, we'll say that this is the inverse. It will not matter which order you multiply them in. We'll get that, but let's just go through this example. So let's just do our normal dot product or inner product multiplication. Right, so I'll leave the 8th out the front. So there's a 4 times 3 plus 2 times minus 2. That's the first piece. And then over here we have a 4 times minus 2, right? 4 times minus 2 here. And then plus 2 times 4. Right, good. And then we have 2, 3, 3 minus 2. You might notice something about the way they're balancing. That's a nice thing to see. This is just a 2x2, of course. 3 times minus 2. And then the last inner product is 2 times minus 2. This is pretty fantastic. Plus, I want to write 3 times 4. All right, so let's look at what happens here. So here and here, we've got, in this case, minus 8 plus an 8, so this is 0. And this is 6 minus 6, so 0. 12 minus 4, that's 8. And then minus 4, 12, 8. So this is looking very nice. And if we multiply through by the 1/8, we get 1, 0, 0, 1. And this is the identity matrix for 2x2 matrices. So identity matrix times any 2x2 matrix will give you that matrix back. And any matrix that you can multiply it with, it will not change it, right? So it's like multiplying by 1, right? So this is 1 for 2x2 matrices, quotes. Multiplicative one, right? Pretty awesome. So in general, so identity matrices, so the identity matrix, matrix I, we don't really leave it there, but you can write sometimes an in. So this is for n by n. Leaves matrices unchanged under multiplication. Oh, there's a lot of good things we can say here, but let's just do, right, so 1, 0, 0, 1 times maybe, 2, 3, minus 1, 4, 2, 1. I want you to think about this from our elimination matrix point of view. What does this first row do to the next matrix that it's multiplying? It says I just want 1 of row 1 and 0 of row 2, which is to say the new row 1 is the old one. So we get 2, 3, minus 1, 4, 2, 1. So maybe use the row operation story here. So this is saying row 1 prime equals row 1 and row 2 prime equals row 2. These are new ways of thinking about things, I guess, if you've seen matrices before, right? So 0, 1 along the bottom says I want 0 of the first row, 1 of the second row, and that becomes my new second row, which just means don't change it. So really nice to see that. So identity matrices don't change things, so under multiplication, so this is what we would have in 0, 0, 0, right? This is I3, this one, and I4. And we usually know what we're talking about with size, so we leave the, I have to write lots of zeros now. So let me just actually indicate sometimes what you might do with this. So if you've got a huge matrix, it's all diagonals, all just along the diagonal, you might just put a big kind of 0 like this. That indicates lots of zeros. Lots of zeros. Very exciting. Sometimes you have to, if it's 1,000 by 1,000 and it's got a nice structure, you have to indicate it by a kind of a pattern. Okay, so good. There's a lot of stuff about the identity matrix. Okay, so let's say we have, right, so given A, if A to the minus 1 exists, so we'll use that kind of terminology a lot. If the inverse exists, then this is true, and we'll come back to this, that A, just as we saw for this little 2 by 2 example, it doesn't matter how big, this is an n by n, right, this is for any size. This equals A times A to the minus 1, the order doesn't matter, so like a third times 3 equals 3 times a third equals 1, that's also true here for matrices. You can have weird things where a matrix might work from one side but not to the other, but we'll come to that again. So, order doesn't matter here. So it's a good, and we've talked about how order matters tremendously, right, for matrix multiplication. And I'm sure you've told all your friends about that. It's exciting. It is. Okay, so that's true, right? So if we can do that, then lots of things can happen. So let's see. So just whether the inverse for a matrix exists or not, just determining that is a big deal. You don't have to calculate it, right? So this is a series of big deals. Okay, so and that's just what I want to list now, and then the next piece we'll have examples. So a selection of big deals. Let's make it blue. This is great. Big deals. Ooh, no. This is a mathematical term, a big deal. There are lemmas and proofs and so on, corollaries, which no one can pronounce properly, and a big deal. Selection of big deals for, let's write this, for A to the minus 1. All right, so, am I going to do that every time? Maybe. So 1, so it's very important if we can just even know, let me write that down. So even knowing if A to the minus 1 exists is variable, right? Right. So that'll kind of come out, right? We don't have to. We may not have it, right? So we may not have the actual form. We just know that we can undo A. Right. This is a bit of a silly thing I'm doing. Okay, so there's one. Let's make it a different color. Good. And then a second one. All right, so this would seem like this is the end of the course. Okay, let me finish the course. Done. Okay, done. We're just going to finish it. 20 lectures ahead. Let's do it. All right, so if you've got a to the minus 1 exists, then we can do this. This is good, right? Let's take ax equals b. This is our wonderful friend we're interested in, apparently, right? So let's say what these are. This is m by n, m by 1, and this must be an n as well, right? So in this case, m equals n. All right? M equals n because we've got a square matrix. So if that's true, then we could put a to the minus 1 at the front. We're going to pre-multiply both sides. Order almost always matters, right? So we have to pre-multiply. Pre-multiply both sides. You know, no sliding around of matrices. Some of you will do it. You will be sad. You will become sad if you do that. Please don't do it. So we're pre-multiplying both sides. So what happens here on the left? Awesomely, that's just the identity matrix, right? So this is the identity matrix on the left times x equals a to the minus 1 times b. Identity matrix times anything, as long as it's well defined. This is just x, right? 1 times 3 is 3. Looks like that. Done. So we're done. We're finished. That is it. As long as we have an inverse, we're good. All right, so problems are, we're often going to be very interested in rectangular matrices. And 2, it's very hard to compute the inverse even if we can, right? Okay, so problems. Thanks for coming is what we could put here. But wait, eek. So there'll be things later on where you get your free set of tofu knives for doing something well, right? So, you know, it turns out that solving things a certain way gives you all these other benefits. This is one where there's a big block waiting for you. Many systems, oh my gosh, systems have rectangular A's. I know a square is a special rectangular A's, right? So m not equal to n, so no inverses. Also a to the minus 1, so there's this. A to the minus 1 might not exist. So that's fine. That's actually going to be a healthy kind of system in some ways. Very important kind of thing. A to the minus 1, and just so many things will come together. My gosh. All right. I have to stop myself from telling you all the goodies. All right, one of them is the pivot. You'll have at least one pivot that's 0, and at least one eigenvalue that's 0. Incredible. Okay, let's not write that down. I've given away too many secrets. Too many secrets. Yeah, as the semester progresses, we move to wearing cowls and that sort of thing. But you not there yet, grasshoppers. Okay, so sorry, and I know that I should have. I've written the wrong. I've completely written the wrong thing. Too excited. May not exist. And then even if it does, even if a to the minus 1 exists, computing a to the minus 1 is very hard. It's very hard work. Computationally, right? And it gets worse as you increase n, which, so we won't exactly say, but grows badly with system size, with n. It gets worse and worse and worse. So we try to avoid it. So we actually try to avoid it. All right. These are good things to have learnt at this point, even though we're very excited. Okay, so I'm going to move on to some kind of surprising little pieces here about a to the x equals b. All right, and then we'll wrap this up. All right, so there are a few things there. Okay. And this will be all reinforced in many, many ways. All right, so let's say a to the minus 1 exists. This is more about ax equals b. So these other things notwithstanding, let's keep going. Then ax equals b, we've seen this a little, we've been talking about this sort of thing. Ax equals b has one solution, has only one solution. And this is true always, right? Which is to say for all b. I know I keep going on here. So any b, there's a solution. So why is that? So simply, we can just, we do what we did before, right? So it's on the previous page, so I don't need to write it. X equals a to the minus 1 times b. Right, so there's you put a b in, you get a unique solution x, right? Boom, it's a little factory. Put a b in, it's like a sausage machine, and it goes and makes an x. There's one solution. All right, so that's interesting. So we know there are 0, 1, and infinitely many solutions to these linear problems. And so if a to the minus 1 does not exist, that's when we get into these other ones. So big deal. So if a to the minus 1 does not exist, we don't have it, right? Can't make it. Right, then we may have 0 or infinitely many solutions. The other cases. Good. So that is a big deal. We'll come to that. We're going to come back to that, right? That's going to. So this is a more later situation. We can't quite see what's going on there yet, so it's a more later situation. Everything is a more later situation. Good, good, good. More things. On the other hand, okay, so this is good. So if, and this is sort of funny notation perhaps for some of you, if there exists an x not equal to 0, right? So in brackets, I'll just write this. So this is, there exists, that's what that backwards e is. There exists an x not equal to the 0 vector, right? Very important that that's a 0, right? It's a 0 with a little hat, that's a vector. Right? If we're in n dimensions, it's a, so let's say 0, 0, dot, 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 0. Right? That's important. Don't get lazy with your zeros, you need to distinguish them. So if that's true, right? So if we have an x that's not equal to 0, yeah, such that a times x equals 0. So if you like, a sends this x to 0. So this is a maps x to 0. Right? So x is not equal to 0, it just goes scrunches it, right? Crushes it. Or a crushes x. Something like that. Then the inverse doesn't exist, right? So this is we're winding this out a little bit. There's a very simple proof. Then a to the minus 1 does not exist. So we're going the other way here. We were saying things about x, depending on whether a or a to the minus 1, or whether the inverse existed. Now this is something about a property of x, solution. So it's a very special kind of x, all right? And why is that? Well, let's give it a, I'll put a little subscript here. We'll call it, no. All right, let's wait. Sorry. So let's just say we've got this x. This is true. So a little proof, lots of tiny proofs in matrixology. This is true, right? True. And then we can multiply both sides by the inverse. That's fine. There's nothing wrong with that. See, I didn't put a hat on it. Right, so this is blue. This is an n by 1. This is an n by n, n by n, n by 1. This is an n by 1, and this one's an n by n. Everything's good. This, of course, is the identity times x. And any matrix times the 0 vector is 0. So this is identity times the vector is itself. X equals 0. But this is a contradiction, right? Right, we started with x. X was not equal to 0. And we've shown that x is equal to 0. So this can't be true. So we can't, so a to the minus 1 cannot exist. That's what this is. A to the minus 1 cannot exist. Otherwise, we'd be able to show that x is equal to 0. Okay, so this is a little, let me foreshadowing, little, I think I can say that. There's plenty on these slides now. Foreshadowing. So that was good. Foreshadowing is that if ax equals 0, we say x lives in the null space of A. This is the null space of A. We're going to talk about it again a lot. It's a big deal. This is a right null space, left null space. So these are all the vectors that get scrunched by A. All right? That's going to matter a lot. Okay. Another good thing. What's another good thing? I have a list of good things. Foreshadowing is always good. I like it. Yes, so this is a good thing to know. So if we multiply two matrices together and take their inverse, think about how this might work out, right? So it's an n by n, two square matrices multiplying each other. How do we undo them given we might know what the inverses of A and B are? Well, so this is going to pop up a few times, this sort of structure. It's b to the minus 1 times a to the minus 1. So why is that? Because we're trying to undo this, right? We're trying to multiply that by something to undo it. And so let's look at that properly. So we can see this if here's our inverse, just multiplying from the left. So these two hit each other. So we can see this, and it doesn't matter which, right? So we could do it from the right-hand side. It's great. So these two hit each other. In this case, it's the B's that hit each other. So let me just work through. So these two here, they become I. So this will become b to the minus 1. And I'm just going to write out the whole thing times the identity matrix times B. In this case, it'd be A. And then this stuff is replaced by the identity matrix. And then a to the minus 1. Very important. And then this is identity matrix times anything is the identity matrix. So this is just b to the minus 1 times B. Would absorb it, right? You could take IB and replace this by B. And if you want, it doesn't matter which one you do. We could say this is equal to A. So this is A times a to the minus 1. And both of these are exactly, this is the definition of the inverse. So you reverse orders. So if we just kept going, so say we have A, B, C, D. Then to do the inverse of this, you have to undo the A, then undo the B, then undo the C, then undo the D. if you're multiplying from the left, and the opposite if you're multiplying from the right. So that gives us, we just flip the order: d to the minus 1, c to the minus 1, b to the minus 1, a to the minus 1. Okay, good. Good thing to know. And that's just by thinking about how these things must behave. What else can I tell you? I think the last main thing to say is that, and this will matter later on just for a little bit, if we have these guys, if we have A and we have a Z, Z's are fun to write, left, we'll call it, and ZR, and these are all n by n, such that this is true, that A times ZL, that should be ZR, if we put it on the right, equals Z. So if, let me say this, if this is equal to the identity, and Z left times A is equal to the identity, then, right, so the words might be, the word would be, it's a right inverse. So let's say we have a right inverse, it undoes, right, because the multiplications are different, and we have a left inverse, then they have to be the same matrix. Then the inverse matrix has to be equal to both of them. There has to be an inverse, and it has to be both. So why is that? Another little proof or reason. We're not even going to use the word proof. It's just sort of fetish behavior, you know, fetishizing things. Sorry. Okay, let's do it. So we've got these. So these two things are true. Someone just tells you this. They say, oh, okay, here is a matrix A. I have a square matrix that goes on this side, gives us the identity if we multiply them together, and I have another one that does this. So let's take one of them, this guy. So we can multiply both of them, both sides, by Z left. Right, so this is pre-multiply. Yep. And the right-hand side is going to be ZL times the identity. All right, so we've got both sides. This, of course, is just ZL on the right. And then we're going to use Z left times A. This is equal to the identity. So now we have the identity on right there times ZR equals, and this is of course just ZL times identity is just ZL, and we can just absorb that. So the right inverse is equal to the left inverse, and therefore they must be an inverse, because an inverse does this, right? An inverse does this. It has to be an inverse from both sides. So if someone tries to sell you an inverse and they show you it only works from one side, be very careful. Okay, don't buy those things. I'm here to protect you from bad people in the matrix world. E5 page. No. We've got a bit to get through with these inverses, but that's a good start. We have to compute them. That's what's next. And as I said, the big deal is that, yeah, all right, so we'll start with the next. The big deal is that we can use Gaussian elimination. It's very, very nice. And we will solve this. We'll start with this character that we had here, and we'll find its inverse. Okay, so inverses. Definition, boom. And then all of these goodies, right? It's useful to know it just exists. If it exists and we have an n by n system, ax equals b, we can solve. Of course, it's hard to compute, as it turns out, and many systems are rectangular. If it does exist, there's only one solution for every b. That's a nice thing. And if it doesn't exist, that's when we get the zero infinity, so that's an important thing. And as I sort of suggested, that'll be to do with pivots being zero, eigenvalues being zero, weird. And flipping things around, if there's an x that a maps to zero, a non-zero x that a maps zero, because a times zero equals zero, but a times something's got a bunch of numbers in it that aren't zero, goes to 0, then we know that in fact the inverse doesn't exist, because otherwise you'd be able to, you'd be able to solve for x, and you'd be able to show that x has to be 0. And then null space is what we're going to get to there. Then the rules here for creating inverse, if you've got a bunch of inverses, bunch of separate matrices, and you compose them together, multiply them together, that's a nice thing to be able to see. And then last we have this piece about if we have an inverse on one side, an inverse on the other side, left and right inverses, they must be the same. Okay, good.